All right, welcome back. Before we get started, I have a quick question. So I have my last year's midterm exam available. Do you want me to post it like today or next Monday? So raise your hand if you want it today. Okay, I'll post it later today, just as a practice and reference. But things might be very different this year because last year I made some mistake in making my midterm exam too long. But nevertheless, I'll post it today. Welcome back to our entropy lecture. So this is going to be our second lecture of chapter 3. So in our last lecture, we went over the very long term of the second law of thermodynamics. We also went over definitions of like heat engine and what does efficiency mean in a heat engine. And then we went over a specific case called Carnot cycle. So today we'll extend whatever we learned from Carnot cycle, which is a special case, into the more general any reversible cycle to give a final definition of a new state function called entropy. And then for the rest of today's lecture, after the definition of entropy, we'll go over several examples on calculation of entropy changes in different scenario and setup. So that's going to be the goal of, everything of today and also next Monday. And then next Wednesday, we'll go over a review on all the topics we went over. So at the end of my next Monday's lecture, I'll do a quick poll, say like which topic you want me to spend more time to go over before our midterm exam. All right, so getting started. Last lecture, remember we went over a specific type of cyclic process called Carnot cycle. Right, so some of the things you want to know that when we say Carnot cycle, effectively what we're saying is a specific reversible cycle that consists two isothermal processes and two adiabatic processes. Right, we went over the derivation of this figure, saying like we know the first step is isothermal expansion. So since it is an isothermal expansion, imagine we have ideal gas. For isothermal expansion, my temperature remain the same. Now it's an expansion, so system is doing work on the surrounding, volume goes up, and in that process, the W is negative, Q is positive, and we plot it in the position where volume goes up, pressure goes down. All right, so in this process, like think about it, do we know like what is the sign for work? What is the sign for heat? How does delta U change for every step along the way of the Carnot cycle? With that in hand, we went over the process and used a little bit of calculus to find out that throughout the Carnot cycle, the differential of Q over temperature integrate to be 0. All right, so this is the part we went over and decide, okay, so using Carnot cycle, using our first law of thermodynamics, we find out that dq over t, the cyclic integral of dq over t must equal to 0. So that gives us one more thought. It's like, okay, so now we have something whose cyclic integral will vanish for this process. That tells us that, well, my dq over t appears to be a state function. But right now, we only went over dq over t for the Carnot cycle. We want to take it one step further and see if we can generalize this conclusion that we find out for the Carnot cycle to any reversible cycle. So that's our first goal here. So now instead of having the Carnot cycle, which remember is constructed by two isothermal processes and two adiabatic processes, now we want to consider an arbitrary reversible cycle. So I'm using this blue curve here, just representing any random cyclic process. It doesn't need to be a circle. I just made a circle so it looks prettier. Now on the PV diagram, like what we did for the Carnot cycle, what we have here, so each of these dashed line, that's what we called adiabats. So what that means is at any point along this gray dashed line are adiabatic processes, right? So if we have like random points on B and D, so as long as these 2 points are along an adiabat, we know that the process connecting B and D are adiabatic processes. And same applies to A and C, M, R, and N, S. So any points along that gray dotted line are like adiabatic processes. In addition, we can also find out curves that are isotherms. So like adiabat, so any of these green curve are curves suggesting, hey, anything along this green curve are isothermic processes. So right now I'm making it like quite small. So if I elongate it into like a longer line, right? So anything along this green curve will be isothermic processes. They can be anywhere. I just like randomly draw them, just say like, for these curves, you can find curves that are isothermic to each other. And that statement is generally true. You can always find something that's isothermic with each other in a PV diagram. Because remember, pressure, volume, and temperature, these traits are interconnected with each other. All right. Now, we're going to go over it one by one. So when we think about the process of our Carnot cycle, we went over several terms, right? We have our delta U, which is using our first law of thermodynamics. We have our work and Q, right? So in this case, when we're thinking about W reversible, so we're going to focus on this W reversible term first. What do we have? For reversible processes, we're taking the integral of this negative PDV. So WREV equals to negative PDV, the integral of negative PDV. So on the PV diagram, taking this integral of the PDV basically is trying to find out what is the area below the curve on this PV diagram. All right, so what that means is when we're finding the area below the curve, let's imagine we're looking at the area below our AB curve, like the area below my AB curve. Let me use a different color. And also an area below my MN curve. So when we're thinking about these processes, we're manually set that the area below this A, M, N, and B, so it's like this zigzag area below that curve, is going to be the same as the area below my AB curve. Now, these lines are not helpful. So the way to put it is if we look at this part below, right? So everything else it remains the same. If we're thinking about the area below my AB curve, which is like this little triangle, and the area below my A, M, and B, so when they're like infinitely close to each other, these areas will be the same. Okay, so like this little triangle, and then this little part plus the AM and B, AM and B. So that this little part plus this little part. So the area below my AB and the AM and B are gonna be the same. Or the other way to put it is we can say that WAB equals to WAM and B. And the same applies to this bottom section. We're setting the WCD equals to WRCDS. Yes.
When you say A, M, and B, like, is it the area of the triangle A, M, and then?
So let's see, A, M, N, and B. So that's the curve. And we're just thinking about the area below this curve. And again, like the way we draw it, that doesn't matter. You can draw it in different way. The point here is we want to have Mn and Rs on an isotherm. And then at the same time, Am and Bn are on adiabats. And then we're just trying to find like points on there so that this condition is true. Like these adiabats and the isotherms, they can be like really, really close to each other. They can be far away from each other. It's like just basically all the lines that's taking the space on my PV diagram. But nevertheless, the first condition is we find points like Mn and Rs, like these are my isotherms. And then the area below my Am and B and below my AB are the same. Area below RCDS and the area below CD are the same. So we're finding points so that the WAB equals to WAM and B. And the same as WCD equals to WRCDS. The next one, when we're thinking about, we went over W, then let's look at our first law of thermodynamics. Now my U, or internal energy, is a state function. So naturally, the state function itself is path independent. So what that means is we can say that delta U for the circle AB will definitely equal to delta U for the circle AM and B. This one should be CRST. 1 second. All right, so the whole point here is we're talking about my internal energy being a state function. So as long as my initial point and the final point are the same, the change of my internal energy must be the same. All right. Now the next one we want to use is taking these two together. We know our first law tells us our delta U equals to W plus Q. All right, so because my delta U equals, so here's the logic behind. So when we say delta U AB equals to delta U AM and B, and that equals to WAB plus, or let's do it this way. So UAB equals to WAB plus QAB. UAM and B equals to WAM and B plus QAM and B. With me so far, just using the first law of thermodynamics. For any path we defined, the total delta U is the same, and then the work and the Q are defined based on the path they're taking. So since in our first part, we went over the derivation to say, we set that the WAB equals to WAM and B, and then using the state function, we have the internal energy AB, the change of internal energy AB, equals to the change of internal energy AM and B. So that these two together tells us we must have QAB equals to QAM and B. So far so good? Just using the setup we have and also the first law of thermodynamics. Now, the next step, if we look back, some of the things we know, right? Just focusing on this little triangle. We said that AM are on the adiabats. BN are also on the adiabats. So remember when we have terms on the adiabats, I'm going to do the following on the board. It might be easier to have this figure available for you. So what we have so far is QAB equals to QAM and B. And because my AM and BN are along adiabats, we have QAM equals to QBN equals to 0. Because my AM and BN are adiabatic processes. And then my AM and B, now AM equals to 0, and B equals to 0. So my QAB is effectively equals to QMN. We don't need to know like what is the heat transfer between A to M. We don't need to know what's the heat transfer between N to B or B to N, vice versa. So my QAB thus becomes QMN. And the same applies to the bottom triangle, or we have QCD equals to QRS. Yes?
I'm still confused on how we know the isothermal expansion.
So in this case, what we're doing is these are the lines for my adiabat. These are the blue dots represent isotherms. So on this PV diagram, we have infinite amount of isotherms you can think about. You have infinite amount of adiabats you can think about. These are just like lines we draw. They don't necessarily need to be parallel with each other. So what we're doing is on this cycle, we want to find 2 points that fulfills 2 conditions. Well, 3 conditions. The first condition is these 2 points, R and S, are on my adiabats. At the same time, my R and S are also on my isotherms. And then these numbers were set to be the same. So because we have like so many different lines to each other, you can always do mathematical operation to try to find 2 dots that fulfills our 3 requirements. So like this one is one of the given conditions, like drawing points on my isotherms and on my adiabats, so that the area under the AM and B and the area under AB are the same.
Okay, so is CD and RS, are they perpendicular to each other?
Not necessarily perpendicular to each other. They don't have to. Again, my drawing here is just an illustration in what that's going to look like once we fulfilled all 3 criteria.
Okay, so that's just a given.
That just gives us the W, the work on AB equals the work AM and B. But using this condition, we can then derive my QAB equals to QAM and B. And because we manually set them to be on my adiabats, we have the rest of the derivation. Okay, next up, what do we have here in the rest? If we look at what we have in here, remember what defines a Carnot cycle. Now this is a reversible cycle, so all processes are reversible, so that one is checked. So my Carnot cycle is defined as 2 isotherms and 2 adiabats. Right, so in my diagram, my MN and my RS are my isotherm. My AC, BD, MR, and NS are all on my adiabats. So we have my Carnot cycle, or MRSN. That defines a Carnot cycle. All right, so thinking about it, MN and RS are my isotherms. MR and NS are my adiabats. So the cycle MRSN is thus a adiabatic Carnot cycle. So far, so good. And then using what we know about the Carnot cycle is the cyclic integral of dq over t will vanish to be 0. And for this Carnot cycle, now AM and BN are, well, for this Carnot cycle, what we have is the QMN equals to TMN. So the QMN, so in my Carnot cycle, we have our M, R, and S and N, right? So my MN has a specific temperature. Let's call it TMN. These two are isotherm to each other, so the temperature is not going to change. On the bottom, we have our TRS. Now, RS is only isotherm, so temperature is not going to change. My heat between M and R is 0, between N and S is 0. So effectively, this cyclic integral just becomes QMN over TMN plus my QRS over TRS. All right. And in here, we just demonstrated that my QMN equals to QAB, my QCD equals to QRS. So that equals to QAB plus TMN plus QRS over TRS. And then what we want to do is imagine a scenario. Now we have adiabats like this. And we want to move these adiabats like infinitesimally close to each other. So A, B are super close to each other. Now we're moving R and S super close to each other so that we can get our temperature TAB equals to TMN and also TRS equals to TCD. So again, this part, one of the abstract nature of it is these adiabats, although I draw it like this, they don't necessarily need to be like a distance from each other with a certain like gap in between. They can be like infinitesimally close to each other. We're just thinking about like any processes that are adiabatically, that are connected by adiabatic process. So what we have is moving the isotherms together, we can find situation, we can approximate that the temperature of my AB curve is the same as my temperature of my MN curve, and the temperature of my RS term is the same as my temperature of the CD term. Yes. So this one is set. All these gray lines are these are adiabats, right? So for adiabats, we're just manually say like for the cyclic process, these lines represent adiabatic processes. So any dot on the curve that are connected to each other, these are adiabatic processes. And then the green ones are when we're trying to find my MN and RS on the PV diagram. We'll manually set them to be on an isothermal curve. So, and then find the same area below like AM and B and then AB, etc. So these were like also set. So it's not like I know it is, it's more like after drawing the, it's not like I know it is isotherm on this diagram. This one is a hypothetical diagram. It's not even a real cycle. But for a real cycle, mathematically, you will be able to find a dot that's on the isotherm. Yes?
You said MRSN is a Carnot cycle, but the first step of Carnot would be isothermal expansion, but M to R, isn't that an adiabatic expansion?
M to R, well, so here's the thing. We have the Carnot cycle as a reversible cycle construct with two isothermic processes and two adiabatic processes. In the example we did, that we say the first step is an isothermal expansion, but that's not necessarily always to be the first step. as long as you have two isothermic processes and two adiabatic processes, that's a Carnot cycle. It doesn't matter how I write it, right? So if we can write it as an isotherm, I can write it as MNSR, right? So it just like depends on how we draw it.
Okay, yeah.
Now with this in hand, the next step is quite obvious. We have the overall cyclic integral of my dq over t that equals to my QAB, QAB over TAB plus QCD over TCD, and that goes to 0 for this process. All right, and remember when we're talking about infinitesimal strip like AB or CD, now let's replace these AB and CD with their actual identity, which are infinitesimally small strip on a random reversible cycle. So that gives us the overall integral of dq over t equals to 0 for any reversible cycle. Any questions before we move on? So in this part, what we're trying to do is, again, taking what we know, which is Carnot cycle, and thinking about from any reversible cycle, is there a possibility we construct a like mini version of my Carnot cycle so we can use something that we derived before for Carnot cycle into any reversible cycle? All right, and then later on, what we have in this case is we defined a new state function. So instead of specify the state function for Carnot cycle, what we have is that dq reversible over t. Now this is a new state function we defined. And this state function is called entropy. All right, and again, when we're talking about the definition of entropy, keep in mind that ds only equals to the dq over t for reversible processes. We cannot drop that reversible process. And what about delta S? What kind of expression can we write for delta S? So in this case, like what we said, we have ds, delta S equals to S final minus S initial. And that is the integral of my dq reversible over t from state 1 to state 2. Keep in mind, we cannot write that 1 over t out because my q reversible might be dependent on temperature. So depending on the situation, we may not be able to write that t out from the integral. All right, and one more question here. We now have the state function entropy. Is it intensive or extensive? Now, temperature is an intensive property. What about heat? Right, so heat is extensive. My temperature is intensive, so my delta S is a extensive state function. So if we rephrase our second law of thermodynamics to say, like, why do we need the second law of thermodynamics? Remember, in the beginning, we defined temperature which is a state function based on our zeroth law of thermodynamics. Saying like two objects are in thermal equilibrium with each other. Well, if object 1 and 2 are in thermal equilibrium with object 3, object 1 and 2 must be in thermal equilibrium with each other. And the measurement of their thermal equilibrium is the temperature. That's our zeroth law of thermodynamics. First law of thermodynamics, we have defined our internal energy, right? Delta U equals to Q plus W. And in here, in our second law of thermodynamics, we used our second law of thermodynamics to first prove that a reversible heat engine is the most efficient one. And by studying a reversible cyclic process or Carnot cycle, we find out there exists some property dq over t whose cyclic integral vanish for a Carnot cycle. And in this lecture, we went over a derivation to demonstrate that for any reversible cycle, we can construct an effective Carnot cycle from that reversible cycle. And as a result, this dq over t, we then generalize it to say like, hey, this dq over t is always going to be a state function that we define as entropy as long as the q is a reversible, is from a reversible path. All right, with me so far? And now we have defined our entropy. We want to know how exactly are we going to use what we know about entropy to calculate entropy change or delta S for different processes. We did this for our enthalpy and internal energy, heat and work at the end of our first, our chapter 2. And in today, later on, we have like 20 minutes left. And also my next Monday lecture will go over a series of calculation in how to calculate entropy change for different processes. Let's get started. The tricky thing about calculating entropy change is, remember when we talk about the definition of entropy, we have ds equals to dq reversible over t. So this dq reversible over t tells us like, even if between my state 1 and state 2, my delta S is always the same between my state 1 and state 2, we must be able to construct a reversible path so that we can calculate dq reversible over temperature. All right, so different from our previous situation when calculating delta U or delta H, you only need to identify initial and final state and then we're ready to go. But in here, when calculating delta S, on top of identify our initial and final state, 1 and 2, we want to somehow be able to build a reversible path from 1 to 2. And then we can calculate delta S using the integral. So let's see some examples together. We might not be able to finish all of them, but we'll see how far we go. First of all, a cyclic process. What is delta S for a cyclic process? It's going to be 0 because it is a state function. It's the nature of the state function tells us delta S must be 0. Well, yes and no. So in this case, even if my delta S equals to dq reversible over t. So if you want to use dq reversible to solve that integral, you must build a reversible path. However, we know that the nature of entropy is the state function. So because we have already proved that S is a state function, delta S will always equal to 0 for any cyclic processes. All right, next up. What about reversible adiabatic processes? Now that represents my 2 adiabats on my Carnot cycle. You can write it out. We have, well, ds equals to dq reversible over T. And for my reversible adiabatic processes, what do we know about heat transfer? Q is 0. So in this case, my dq reversible equals to 0 because it is an adiabatic process. And as a result, my delta S is also 0. All right. Next one. What about reversible phase change at constant temperature and pressure? So whenever you see phase change, basically it tells us we want to know the enthalpy for that phase change or the delta H of the phase change. That's something we can find by looking at thermodynamic tables. So now in this question, how do we solve this problem? Again, what we want to write out is first the definition of my delta S equals to 1 to 2 dq ReV over T. A few things we know from reading the question. We know for this reversible phase change, it happens at constant temperature. So we can take this temperature out from the integral. It becomes 1 over T, 1 to 2 dq reversible. Right, or you can write it as QREV over T. Now, what is my Q reversible for this process? We want to use another thing that we know. We have it happen at constant pressure. Now, at constant pressure, my Q or QP equals to something we know. Remember, we went over derivation to give enthalpy a physical meaning. So at constant pressure, my QP effectively equals to delta H for this phase change. Or taking them together, we can write delta S equals to delta H over T for reversible phase change at constant Tp. So some kind of example question for this setup is, again, instead of telling you this is a reversible phase change at constant Tp question, you might encounter this kind of question. If we read it, we're saying the heat of vaporization of water at 100 degrees Celsius is 40.66 kilojoule per mole. Find delta S when 5 grams of water vapor condenses to liquid at 100 degrees Celsius and 1 atm. Right, so reading the question, we can write out, what do we know? We can write out delta H of vaporization equals to 40.66 kilojoule per mole. Temperature equals to 100 degrees Celsius. Now, when we set up this problem, we want to have the delta H of condensation, because that's what the question is asking for. So delta H condensation equals to negative delta H vaporization, which equals to the negative 40.66 kilojoule per mole. Then we can consider the situation. It's specified the phase change is happening at 100 degrees Celsius and 1 atm. So this is effectively telling us my temperature and pressure are kept the same at 1 atm and 100 degrees Celsius. So we can use the equation we just derived. So delta S condensation equals to, well, delta H over T, which equals to negative 40.66 kilojoule per mole over temperature. And whenever you encounter temperature, always use Kelvin for this class. 273 plus 100 Kelvin. And that gives us, you can plug in your calculator, but the number is negative 109 joule per mole per Kelvin. Cool. All right. One more step. The question is giving us for 5.00 grams. So instead of 1 mole, just calculate the number of mole in that 5 gram and then finish this calculation. Which is 5 gram is like 0.278 mole. And that's negative 30.2 joule per Kelvin. Okay. Next one, we have our reversible isothermal processes. So this one we already sort of mentioned it. So this one we can simplify our integral for delta S equals to 1 to 2 dq reversible over T. That's because it's at constant T, we can take the temperature out, becomes 1 over T, 1 to 2 dq reversible, or q reversible over temperature. And for these isothermal processes, for ideal gases, we can again use our first law of thermodynamics. Let's say assume ideal gases. Then for ideal gases, my isothermal processes, again, we have delta U equals to 0 for ideal gases only, for isothermal processes. And knowing the change of volume and pressure, the change of volume and isothermal, we can calculate the work that's being done by the system to the surrounding, and Q reversible equals to negative of that W reversible. And hence, we have a way to calculate my Q reversible. How are we doing so far? We went over like 4 bullet points so far. Just want to make sure we have any questions. Okay. Next one, isobaric heating with no phase change. So in this case, we have to assume a hypothetical path. So the first thing is to assume hypothetical path, or assume very slow heating. Or reversible heating. So at constant pressure, again, we have dq equals to dqp equals to delta H or Cp dt or dH. And then the delta S of this process between a random state, 1 to 2, thus becomes my Cp over T dt. And again, this is at constant pressure, no phase change. Yes?
For the other one, like the other one that had constant pressure and constant temperature, you can just do CP, like.
So the other one is a reversible phase change. So phase change is different from change of state. So these are two different things. A phase change means we have processes like liquid go to solid, solid go to gas, gas and go to liquid. So a phase change, meaning our system of interest undergo a freezing or vaporization or fusion. This kind of processes are called phase change. Change of state is a different thing. So in this case, when we say a isobaric heating with no phase change, we're talking about, hey, the phase of my system remain the same. It's a liquid, it remain a liquid. It's a gas, it remain a gas. And we're talking about the change of the thermodynamic state of my system without a phase change. So a phase change is like a cup of water freeze into ice. So change of thermodynamic state is I have a cup of water at 20 degrees Celsius, I heat it up to 80 degrees Celsius. So these are two different things.
Okay, but for phase change, would you do Q to CPDT?
Now for phase change, my dt is 0. So we don't use, we still use this one, the QP equals delta H. But delta H of the phase change is the enthalpy of vaporization or fusion. Because when the phase is changing, my temperatures remain the same. It's irrelevant to say like CPDT because that CPDT equation refers to the change of a thermodynamic state. So in this case, the example question would be giving we have delta S, find the delta S of 100 grams of water that is reversibly heated from 50 degrees Celsius to 75 degrees Celsius at 1 atm. We also need to give you the Cp of water. So in this case, we're giving you Cp of water is constant at certain temperature. We might also give you Cp as a function of temperature, so you can actually solve that integral, right? So different ways, but we need to give you information about what is Cp. And then setting up this question, since Cp is a constant, my delta S equals to T1, T2, CPT dt. Now Cp takes out and just becomes ln T2 minus ln T1. You can plug in the numbers to get a result for this question. All right, I'm gonna save the rest of my lecture to our next Monday. So in our next part, we'll talk about like say number 6, right? So in general, we don't specify any like pressure, volume, temperature to be constant. We just say in general, what is the change of state? How to calculate entropy of change of state if we know it is an ideal gas. And then we'll look at scenarios like, for example, if we have irreversible changes, how can we build reversible path to solve the problem? And then we have, irreversible phase change and see how can we build reversible paths for irreversible phase changes. So these two are going to be a very good demonstration. And what does it mean when we say build a reversible path? And at the end, we'll look at a special case of, say, mixing different inert perfect gases at constant T and P. What is the entropy for this mixing process? And from here, later on, we'll use this as a demonstration to review like what exactly is entropy. What's the physical meaning of entropy, which is right now very abstract for us. All right, so this part, hopefully we can finish by next Monday, and then we'll pick up the physical meaning of entropy after our first midterm exam. All right, that's it for today.